Hello, in this video I'll explain to you in 10 minutes my master's work, Online Reconfigurable Convolutional Neural Network for Real-Time Applications. For the full details of the research, please refer back to the research paper or the thesis. So starting off with the motivation, with the advancements in technology, smart devices are becoming more and more popular, such as smartphones, personal assistants, and many other devices, and they become smart by using artificial intelligence. And one very common form of artificial intelligence is a neural network. However, a main problem with a neural network is that it's big in size, it's high in computations, and it's not very flexible at runtime. This makes changing the network at runtime very costly and unfeasible. For this reason, we present a reconfigurable neural network that's able to be reconfigured at runtime, in real time. So our proposal is very simple. Given a network, for example, the network here on the right, we're able to remove a couple of layers and then replace these layers by a smaller number of layers. And the network should be able to function, however, for a small reduction in accuracy. But since the network is overall smaller now, it runs much faster than it did before. And how we are able to do this is, given the network, the full network, we're able to remove layers and then replace these layers by a smaller number of layers. And then the new layers are not yet trained. So we freeze the entire network because we only want to train these layers, and then only save these layers. So later on during runtime, we're able to do this conversion in runtime because we only need to load in the new layers and not load in entirely new network. So we look first of all at what other similar research was done in this area. And then one idea that comes up is networks with different sizes. So we can see this in, for example, VGG, where they have VG16 and VG19. YOLO, they have YOLO and the YOLO Tiny. And for example, each of those has a large network and then a smaller network according to the available resources. However, one problem with this approach is it has multiple networks, so it consumes a lot of space and it's not ideal. And then other ideas such as network pruning, where they have an original network and then they start removing parameters to make the network overall smaller. And then I'll go through examples of adaptive neural networks really quickly, such as early exits, where they have, in the example here on the top right, a convolutional network, and then after each convolutional layer, an exit layer. So after each convolutional layer, we can exit if the accuracy or the confidence threshold is surpassed, or the available resources is not a lot, so we can just exit when it's sufficient. Another example would be a slim neural network. So you have a network, and this network is able to function using a partial weights of the network. So for example, you can use 50% of the network or 75%, and then we can choose this percentage according to the resources available. So our idea proposes a reconfigurable neural network that runs at runtime by replacing the layers of the network. It works in real time. It does not require additional space or an internet connection, and it works by doing a trade-off between accuracy and speed. So moving on, to be able to implement our idea, we create two frameworks to help us implement the idea, and they are the model configuration creator and the model configuration loader. So starting with the model configuration creator on the left, basically given any pre-trained model and then a configuration, it removes the layers that needs to be removed from the base model and replaces them by the layers that we need to be replaced, and outputs a trainable configuration, and we can use this trainable configuration to train it. And after it's been trained, then the model configuration creator helps us save only the newly added layers. And then we can see the structure of the layers saved, where we have folders, for example, week 1, week 2, week 3. These folders are showing each configuration we created, and then inside each configuration there are the numbers which represent the layers that we've saved, and then the CFG file which represents the deleted layers. Finally, the model configuration loader on the right is used to load in the configurations at runtime. So given the base model, the directory, and the which configuration we would like to load, it loads in the configuration and creates a model that it's ready to use at runtime. So one important question that pops up is how do we select the configuration? And very simply, we have three rules. First rule is we remove layers from bottom up. So we remove layers from the bottom first and then move layers above them and so on. And we only remove convolutional layers. Next is if there is a convolutional layer followed by a batch normalization layer and we remove the convolutional layer, then we must remove the batch normalization layer as well. Finally, to adjust and change in size between the input and output due to removing max pooling layers, for example, then we need to add back the same number of max pooling layers, or we can add smaller number of max pooling layers with a larger filter size, or we can maybe add the smaller number of max pooling layers and then we can add strides in the convolutional layers that we just added. So to prove our idea, we tested it on 3 different datasets: Cypher10, Cypher100, and Pascal-Vogt 2012. For each one of those, we created a main model and 3 configurations. So starting off with Cypher10, Cypher10 is a 10 image classification dataset. We applied some augmentations to avoid any kind of overfitting. We created a base model based on VG16, and as we mentioned before, created 3 configurations. So as we described, we removed the number of layers from the end, replaced them by a smaller number of layers, and we applied this to create the 3 configurations. Next, Cypher100 is basically an extension to Cypher10, and it's a 100 image classification dataset. We also apply augmentations, and finally we create again a base model based on VG16, create 3 configurations, same as before. Final dataset, Pascal-Vogt 2012, is a 20 class object detection. However, we only choose the person class because of the huge bias that we can see on the bottom left in the class sizes. And again, we apply augmentations, and this time we use YOLO v1 since it's an object detection dataset. So we use YOLO v1 tiny. We use YOLO v1, not any other YOLO, because it's the only one that does not contain skip connections or multiple outputs, which would be confusing in our proposal. And same as before, we create 3 configurations. It's worth mentioning that we've trained everything from scratch, so no pre-trained weights, to avoid any bias in the final output, or to make sure that the results are not biased. So to evaluate the performance of our work, we used accuracy or loss according to the problem. And then to see how much the network became faster, we measured the number of floating point operations, or flops, instead of time, because time could be biased according to the machine. So finally, we set our expectations. We're expecting the base model to always have the maximum performance and the maximum size. And then with each configuration, there should be a trade-off between performance and the number of floating point operations. And this is exactly what we can see in the results. For the results of Cypher10, we can see the test accuracy of the base model starts with 91%, which is the best accuracy. And then with each configuration, it reduces the test accuracy a little bit. However, looking at the floating point operations, it starts with 3 million floating point operations and down to 800,000. So this is exactly what we're expecting, and we can see the same results in Cypher100, starting with 59% and down to 47%. However, looking at the floating point operations, starting with 2 million floating point operations, we're able to reduce it to only 272,000. Finally, with Pascal-Vogt, we use loss since it's a regression problem and not a classification one. So with loss, we can see the base model had the best loss, which is 5.8, and then the loss increases with the configuration 3 having 6.6 loss. However, the floating point operations again starts with around 20 million with the base model and reduces down to around 4 million with the third configuration. Finally, we compare the performance of the switch to make sure it runs in real time. We can see a base model runs in around 2.2 seconds, 2.3, 2.6 seconds for each of the datasets, and the configurations are around the switch between the base model and any configuration is around 200 milliseconds, which runs in real time. So finally, looking at the memory savings, base model, for example, in Cypher10 used up 35 megabytes. However, each configuration used 5.6, 5.9, 2.5 megabytes. So using the 3 configurations together is still smaller than one base model. And you can see the same thing applies to Cypher100 and Pascal-Vogt. Finally, to make sure that everything runs as expected, we run it on an embedded system, which is a Jetson Nano. So we measured the CPU utilization using the base model and after switching in one of the configurations. And we're able to see that in some examples, the CPU utilization was improved by using the smaller model or the smaller configuration. So we finally conclude that we presented the problem that neural networks are by default not very dynamic at runtime. We proposed creating configurations that are able to replace their layers at runtime. We explore similar literature. We created a framework that encapsulates the process of saving and loading configurations. We presented a proof of concept on 3 different datasets. We tested it on an embedded system, and that was it. Thank you, and all the resources will be down in the description.